Hello, thank you very much, George. Hello, everybody. I'm happy to be here, and I would like to thank George for all his effort to go ahead with all this project and giving us the opportunity to come here and present some of our results to you. And of course, we have a great benefit because we have a lot of our students during the exchange, they had the experience of different societies at different levels of technology, and I think that was a very good opportunity for them to widen their minds, and it was a good opportunity for us to have this cooperation. I'm coming from Greece. Greece is the southeast part of Europe, is somewhere here. As George says, we are from the center of Greece. Our town where we are based is Volos. It's a beautiful town at the seaside. You can see the port, and of course what is the best is the combination between the sea and the mountain, which gives a good combination. Is nice. This is our central university unit. We are a new university. We are working for 30 years, and you see this is an old tobacco factory, and our architects have made a combination of the old building with the new glass buildings. And this is our department of agriculture where I'm based. I'm going to talk about soil. You know that soil is the upper layer of the Earth's crust. It is the substrate where we are growing our crops, and of course is the basis of the life of Earth. Our soil was evolved the last million of years and under different, the effect of different factors. So we have different competing activities, erosion, formation of soil, interaction with plants, interaction with climate. So finally, we turn up with a soil which is highly variable. We have a soil which is, has a variability inherent, and so we have to find ways to see how this variability exists and what we can do. So the idea is that we need to know several factors of soil quality, like texture of the soil, or elevation variation, or structure variation, or organic matter and nutrient variation, and compaction variation. All these factors, it is important to know them in order to manage our fields and our soils. So as you already know, precision agriculture is defined as the management of variability of the fields. So since the soil is the basis of all crops, it is important to know the variability of the soil in order to be able to manage our fields. So the key point in our precision agriculture studies is to know what is the variability of the field. So what we are doing, we are taking samples of the soil and we analyze them in order to produce this analysis of the variability. The question is why to take samples of the soil is we need to know nutrient levels, we need pH, we need texture, we need all these parameters of soil organic matter, soil cation exchange capacity, different factors which we have to study, analyze, and try to see how they work. Talking about conventional agriculture, the system was working properly. We had to take samples, we take a diagonal of the field, we take samples, we produce the samples we need, we analyze them, and we accept that all the data are the same in all the field. That was easy. Then we have the yield. We can assess how much nutrients we removed or how much nutrients we need to have the maximum yield. And then we arrange fertilization, we arrange water application, we arrange everything. So that was the easy way. The problem is that when we started measuring yield, we found that variability is high. As George have shown you at the beginning, we found that actually we have places high yielding, and if we consider this mean application of the nutrients, then in this place we have a deficit of nutrients. We have other places with low yielding, so we have a surplus of nutrient. For us in Europe, this is a big problem because our common agricultural policy is requiring to have friendly to the environment attitude, so we need to reduce the fertilizer, reduce nitrogen pollution, and of course, one of the problems is our pocket. We spend money without getting back some yield. So we need to know this variability and try to see how is distributed in the field and build on that different things as there are NDVI measurements and all the other measurements which can be combined and try to find solutions, how much nutrients we are going to apply, how much water we are going to apply, and which way we are going to apply. So how we sample the soil? Obviously, we have two cases. We have a field which we don't know. Then it's good to go there and do a grid sampling. I shall explain what is that. But sometimes we know the soil, we cultivate for many years. We know that there are places which are producing more, places which are producing less. So we can, from the beginning, define some management zones and try to have a directed sampling, and that facilitates us to produce what we want. So what means grid sampling? Means that we are going to have a field like this one, and then there are different softwares. They can provide us with these lines. So we can divide the field either in cells, like this one, small squares all over the field, or we can define these points here, which are the places where we are going to take the samples, and we assess that the properties of the soil are there. So the idea is that we can make a grid and try to get the samples from the grid. One case is to use this cell sampling. You see here the cell. We are taking different samples within the cell. We mix them, we produce one sample, we analyze it, and then we accept that each cell has a certain properties, soil properties, texture, nutrient content, or whatever else we are measuring. So we have a field at the end having different cells which have sometimes same, sometimes different soil qualities, and this is the way we are doing this sampling. Obviously, the second idea is to use the points. Then we take a cross like this one here. We are taking samples around, and we assess that this, the properties of the soil are based in this point. So then we are making, from the points, we have to make interpolation between the different points. So we produce a map like this one. It's not squares, but it is more spread the quality of the soil. So we have several problems with grid sampling, which we have to face. Sometimes we get the grids, and sometimes the cell of the grids are belonging to different parts of the soil, different quality of the soil. So we have to find some solution for that. The second problem we have is that we try, when we have a grid sampling over a non-uniform soil, then we have to find some ways to manage that and not having samples which are not representative of the cell we are taking the samples. So one way to improve it, when we know how about is our soil, we can define management zones. When we say management zones, we mean zones which have homogeneous properties, and then we try in parts of the soil which is less homogeneous, we try to have more samples, and then in parts of the soil which have low variability, we try to have smaller number of samples that save us money and give us more information of the variability of the soil. Another problem usually we have is that we have sometimes when we apply fertilizers, and if our fertilizer is not working well, we produce rows of different application rates of our nutrients. So this is a problem. If we try to have samples like this one, then we produce all this field as it is with high nutrient content, and all the other field is different. So this doesn't give us a good picture. We have to find also a solution for that. And the solution is to try to not to have the samples within each cell, but try to have at different places of the cell in order to reduce all these problems that can happen. You can see here also the density of the samples. We can have a high density or a low density. High density means a lot of cost for analysis, so it's not very convenient for us. But low density means that sometimes we are going to produce different maps. Here you see a grid of 1 acre, which is giving a different picture of the soil, of the field, than this one, which has a 2.5 acre grid, which gives also a different picture of the soil, of the field. So this is something we have to judge, how much we have to pay in order to have a better picture of our field. And this depends on the variability of the field, which most of us we know because we cultivate it, we harvest it, we know how it is, so we can judge what we have to do. So when we are trying to do the sampling, we never go like that, having points after point. Either we have to make a circle around the points, the crosses of the lines. So the largest it is the circle, the best it is the idea. The second idea is to use zigzag to different distances apart from the line, so we reduce any possibility to take all the samples from one row with a certain quality and not depict the real case of the field. So grid sampling is used to delineate management zones. What we mean, if we know we have the grid, we have the soil analysis, we can say that, all right, we can make zones of different texture, or we can make zones of different percentage of phosphorus or potassium or whatever else it is. This is important because we can judge if the amount of nutrients or the quality of the soil is sufficient to have a certain yield, so we can evaluate how much fertilizer we have to put in order to produce a better situation. So we can have these management zones, and then we can build on that and do the management of the variability of the soil, having exactly trying to meet the demands of the different management zones. The second idea is to do a directed sampling. The idea is that we know how our field is divided in different homogeneous zones, and then we take the samples from the certain areas, and this will help us. Because if you consider that you have a map, for example, a yield map, and you have the places which have high yielding, then to have the samples from this place, this can help us to correlate what is the relation between the nutrient status or the other factors of soil with the yield, and that will help us to analyze and understand why we have this variation. And of course, this could be also the basis to do some corrections in order to improve yield. So the idea is that if we know the variability of the soil, and we can divide through another mean, one of them is apparent electrical soil conductivity. We are going to talk a little bit later. This will help us to define the zones and then take the samples from the zone, and that will help us much more to understand what happened. So how to collect the samples? Usually we have either some manual way, or there are some different small vehicles which can be used to take the samples. Of course, the work is tedious, it's not very easy, but we have to do that in order to have all this analysis we want. So analysis is important. To send the samples in a good laboratory, it is better to have duplicated the samples and keep one for reserve, because sometimes some of the results could be wrong, so we can replace it and analyze them again, and that can help us. Now, how many samples we are going to analyze? This is a function of the variability of the soil. The more the variability we have, the more samples we need to have in order to analyze the variability, but at the minimum cost, because the cost of soil analysis is a big problem. Now, this is the idea. We have laboratories. The cost is very high. I don't know how much is here, but I know that in Greece is extremely high to do the cost to do the analysis. So the idea is that we try to find some ways to measure soil properties easily with sensors which can pass through the soil and give us some idea how the soil is. So the basic factor we are going to measure is electrical resistivity. What means electrical resistivity is the resistance the soil presents when we have a difference of potential, of electrical potential, the resistance for the electrons to pass through. And if we take the opposite of that, which is conductivity, then we measure the easiness the electrons pass through the medium, which is the soil, and we can evaluate through that different properties. So the basic thing is that if we consider the soil, you can see that we have three phases. One is air. There is a very bad means for electrons to pass through. So air means very low conductivity. Water is a good means for the electrons to pass. So high water content means high electric conductivity, and the solid part usually is covered by water around, so is a medium means for letting the electron pass. So actually, if we measure the electrical conductivity, we measure most of it water, how the electron passes through water, and of course, this is something we are interested in. But consider that if we have a soil which is a sandy soil, the sandy soil has more air spaces, so it has a lower electrical conductivity because the electrons cannot pass through the air. So the idea is that when we are measuring electrical conductivity, we have the opportunity to distinguish between different types of soil. You can see here that we can measure salinity, we can measure clay, silt, and sand. They have different electrical conductivity values. So the idea is that if we try to measure apparent electrical conductivity, the first thing we measure is salinity. If we have a soil with high salts, then the electrical current is passing easier through the soil, and this is something which is okay. The second is moisture. The third is clay content. So if we have a field, if we exclude the fields with salinity, and we try to have a field with homogeneous moisture content, then most of what we measure, what is the difference we measure, is soil texture. So this is what usually we use apparent electrical conductivity, because with one pass, with one of the instruments we have, then we have a picture of how is the electrical conductivity, what is the clay content, or if you want, what is the texture of the soil. There are other factors like organic matter or some ions or things like that, but their influence is minor. The major influence is the clay content. So to give you a picture of what is the situation, this is some measurements we have done in one of our fields. Very dry. You see values of electrical conductivity very low. This is the electrical conductivity at the depth, much lower. So what we actually did is we had the traveler irrigator, we irrigate it. So what you can see easily here is that what we measure is moisture content. In some way we can measure the quality of water distribution by the traveler irrigator. So this is the idea. We measure moisture content, but moisture content is connected to fine texture soils. So the higher the electrical conductivity, the higher is the clay content of the soil, or the heavier is the soil. So how we measure it? We have two types of instrument. One is an instrument which has electrodes which are coming, which are contacting the soil. it has to be into the soil, a few millimeters. Is the very system which has disks. So we produce a difference potential to the two disks, and then we have the two other electrodes which are measuring the flow of the electrons, and this is the way we are measuring apparent electrical conductivity. We can have disks, depending on the distance between the disks, we can have a measure of up to 30 centimeters, or if you use these disks, we have a measure of up to 90 centimeters. So we have a picture how is the soil and what is the qualities of the soil. This is the instrument. The instrument, most probably you have seen that, is Veris, the interface where we get the data, and you can easily here see that we have a map which is showing the difference. You can see here the different zones at the two depths. You can easily see that we can have parts of the field which have high electrical conductivity, parts of the field with low electrical conductivity. So from the very beginning, we can distinguish zones with homogeneous properties, and this can help us in the management of the soil. This is an icon of a field. George has shown that at the beginning, is the difference in the color. If you have a picture, obviously the color is darker if you have a higher moisture content, or if you have higher organic matter, it is lighter if you have a dry soil. So from the very beginning, also there is some way to distinguish between management zones. The second instrument we have is the instrument which is measuring electrical induction. The idea is that we have a coil here. We are giving electricity, passing electricity through there. A magnetic field is produced in the soil. This magnetic field is causing the electrons to flow. The flow of electrons producing a second magnetic field, which we measure with the second coil, and this is the idea what we are measuring. This is the instrument. It's lighter. You can carry it with you. For us, we have very small fields. Probably this is more convenient. The Veris is much more convenient for larger fields. But we can also put it in some frame. Be careful, you need a frame without any metallic part on that. Any metallic part in the vicinity changes the whole measurement, so we have to avoid that. There are different ideas how you can use it. Of course, there are other instruments under development. There is also this instrument which is measuring soil pH, which can give maps also of soil pH. And of course, there are other development, a lot of proximity sensors, like this one. This is developed in Cranfield University in Britain. There is a subsoiler which can go at different depths. We can regulate the depths by the two wheels. Then we have a lamp which is producing a light, is reflected to the soil, and the spectrum analysis of this reflectance can give us different information. At least the people who are working with that, they insist that they can assess nitrogen, phosphorus, potassium, and different other things of the soil. I don't know how accurate is that, but we are going in the next couple of years, we are going to see how the system is working or not. Now, I shall give you a few data of what we have done in Greece and how we use this electrical conductivity. This is a small vineyard in a slope in Greece, very small, is 1 hectare. But it's convenient to do some work. This is what we did to measure electrical conductivity. We have the M38 placed on a plastic tube, and move it around. So you can see here the data, the raw data we get from electrical conductivity. It is quite clear if you look here that we have one part of the field, which is the lower part of the field. So the field who is receiving all the erosion soil from the upper part of the field. So it's high electrical conductivity, so higher clay content, higher depth of the soil. These are the data we have. Here we have the higher slope, so here we have the lower electrical conductivity, and here there are some differences. So you understand that from the very beginning, when we start going to a field, we don't know the field. If we look to the electrical conductivity, we have a picture of the field, and we can use that, as I told you, to manage the soil. Here you can see this is an elevation map. You will see better elevation map after that. You can see the different levels above the sea here. And here you have the map of the electrical conductivity and how we use it to do directed sampling. We have sampled the different, actually, zones we have formed through the electrical conductivity. But after that, as we are doing research and we have money to spend, we have done also grid sampling to have a better data. This is the measurement, this is the field. As you see, the slope, one slope is this way and the second slope is going this way. We have the electrical conductivity 1 day after rain, and this is 4 days after rain. What I would like to show you is that the measurement is quite stable, so you can use the same data without any, they are constant, so there is no something which is changing from year to year, so we can use that, we can measure every few years and we can use the data. So you can easily see that we have one part of the field, this one, the second is in the middle and another part in the upper part, and you can see the difference. You can see that after 4 days there is a small drop of electrical conductivity, but the shape of the maps is similar. So this is the sand content of the soil. We have developed different maps where we can distinguish the more sandy places and more clay places, so we can use that for the management of the soil. The problem was that this vineyard was organic, so we could not apply different fertilizers. What we have done actually is that we use it to do variability irrigation. Here you can see the map of electrical conductivity and the map of yield. So you can see quite easily that electrical conductivity is correlated with yield. And this is a way to compare maps. One of the problems we have is that how we compare the maps. It's nice to see them and say they are similar, but it's quite difficult to say that how we compare it. So one way is to compare cell by cell and consider how many cells are in the same management zone in the two maps. So finally, we have developed management zones. One zone is this one, second this one, or 3 zones. What we try to do with our farmer, we persuaded him to do, he had drip irrigation system with the lines going from one side to the other. So we persuaded him to cut the drip irrigator tubes here, and so he applies different water this way and different water this way. This helped us to save water, but what was most important is that we improve the quality of the vines, and this was very important for the farmer to improve the quality, because he has also a winery, so for him it was important to have a better wine quality to sell and get a better profit. So trying to conclude, we can say that soil analysis is a tool to assess field variability and explain variability of the field. We have now tools which can give us general picture of the field quite easily and at low cost and very early at the beginning of the season. And based on soil variability and analysis data, we can define management zones and make management decisions which can save us water or fertilizers or whatever it is. Thank you very much for listening.